time 1. It's actually not very interesting, but slightly interesting.
It goes negative.
It goes negative, right? 1 is the point in which I cross from being in positive land to negative land. So I'll put a little dot here, and I'll label that dot t equals 1. Okay, what's the next interesting thing that happens? 3 halves. What happens at 3 halves? It turns around, and so what we're going to do is kind of like add this dimension, right? And I happen to know where I am at time t equals 3 halves. I'm at negative 1/4. Are you following the essence of this? And then this one's pretty boring. Next thing that happens at t equals 2. At t equals 2, I am also back at 0, and then it's just kind of doing this forever. So this is a sort of visual representation with a fake added time dimension of what the bear is doing over time, right? Say cool.
Polar bear.
Cool.
It could be a polar bear. All right, next page. Next page, go fast. What?
10. Yes, that was 4.
Let's do the ground. First one's
What?
back to forward turn.
I was aiming to go like this, and you gave this.
Back to the shop. Forward turn.
I mean, we're
So rule of thumb.
but we still have to analyze it, whether we graph it or not. I mean, I'm not graphing the thing because I don't really feel like I need to graph it.
Can you have negative time?
Analyzing the sign of the, I mean, I don't know, yeah, you can graph it if you want to. You could produce a graph, but then you'd have to graph the position and also velocity and also acceleration. Instead of graphing, I'm just making the number lines because they're telling me the same information to graph with. These are the kinds of questions I mean. Does someone have a real question besides time can definitely be negative. Yeah, we assume by default that time is going from negative infinity to infinity. It said that on the previous page. Oh, he's like done with this page already. Nice.
Oh, I remember now.
That's actually what
Wait, what are you supposed to do?
Did I ask you?
No, but I asked you what are you supposed to do.
And here it just so happens that I don't actually care when the position is positive and negative for this problem, so don't bother trying to factor the position function. But I would take some time in the very beginning and carefully take the derivative, factor velocity, take the derivative of that, get acceleration, factor that, and make nice, neat, overlapping number lines for velocity and acceleration so you can use them later when needed.
Yeah, factor the 3 in velocity. Yeah. Not 3 negative 1.
Let's do it.
Actually, I may have to base for that. Actually,
We did.
factor. Never mind. Does it factor?
Another velocity.
Yes, it does.
Yeah, it's 3.
Positive?
Yeah, but it's really, really worth it to line them up, because the whole point is so you can kind of like the visual. Oh, you didn't do it.
You just don't do do it for the position one?
For this problem, I don't care yet.
The line up with data?
Because they don't ask any questions about like what's positive or moving forward. Well, you're just about that. So no factor around. Minus 1, minus 2. T minus 1, T minus 3.
What do you mean moving left?
I'll give you like 2 more minutes of your board. You can move on to the next.
Right there. Oh, that one. So it's like between 1 and 3 minutes.
Stay on. Stay on. 40, 50 minutes. Okay. Alright, can I do this? Find the position of the object after 5 seconds. In other words, what is S of 5? That sounds hard. I'm going to do this like thingy. Because I'm fancy. Did you get 15? 15 meters. Next question, what is the average velocity? Average velocity on the interval from 0 to 5. That is again the position at time 5 minus the position at time 0 over 5 minus 0. So that is 15 minus negative 5 over 5. So that's 4 meters per second. Yeah? Okay, good. Part C, what is the instantaneous velocity when t equals 4? So they're just asking for a v of 4. So you just plug 4 to the velocity function and you get 9 meters per second. Part D, at what values of t is the particle change direction? Change direction when the velocity changes sign. So that's happening at t equals 1 and at t equals 3. Cool? Okay, cool. Part E, when is the particle moving left? It's moving left when the velocity is negative, so on the interval from 1 to 3. When is it moving right? It's moving right when the velocity is positive, so that's on the interval from negative infinity to 1, and from 3 to infinity. Okay, now finally the only interesting question on the page, pretty much, when is the particle speeding up? We all understand how to do this now, yeah?
Between 1 and 2 and 3 and infinity.
Pretty much, we are going to be speeding up when I'm either moving left and getting smaller, which means more negative, which means speed getting bigger. So that's on the interval from 1 to 2. Or from 3 to infinity, because on that interval my velocity is positive and getting bigger. In other words, speed's getting bigger. And finally, when is my particle slowing down? Answer everywhere else, right? From negative infinity to 1, at which my velocity is positive and getting smaller, so slowing down, and also on the interval from 2 to 3, in which my velocity is negative but getting bigger, which means less negative, which means my speed's getting smaller. Cool? Alright, sounds like you guys are experts on this. If you turn to the next page, you'll see just another example of this. You're going to do this for homework. This one factors the position factors nicely, however, so that means I can ask all the questions about position, velocity, and acceleration. This is basically it's the same thing. This one's doing it by yourself. On the next page is this awesome rocket problem. Blah, 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 model rocket is launched, blah, 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 blah. You're going to read this, you can do this at home by yourself. But just would like to state in advance that I have very high standards for this problem. I say write a paragraph. You need to write like really tiny. The paragraph should be not like 3 sentences, it should be like 15 sentences. Every single facet of this graph has a deep and interesting significance. So really like push yourself to like try to understand the physics of the situation and to explain why everything is the way it is. I want to know why it's positive, I want to know why it's negative, I want to know why it's increasing, why it's decreasing, the concavity, everything has an interpretation, everything has like a sensible story behind it. So it's actually a really cool problem. The more you think about it, the more you get out of it. And then the rest is just like pretty easy. So one of the things you're going to do over break is like finish the packet from the point that we started to the end, which is really not that much work. Let's go over homework. Get some homework due today. We're going to go over, we're going to do as much of it as we can. We have like a 25 to 30 minute lesson. So what's up?
Wait, the point we started to the end?
I'll put everything on deadline, but yeah. I think we'll do the rest like later, but at least from the point, from the point we started to the end, I guess we'll do for homework. Maybe more, but at least that much. All right, Calvin, there was some homework due today. How'd it go? It was on optimization. I thought a couple of problems were easy, but then 3 or 4 were pretty hard. Don't have time to go over every single one, unless we go really, really fast. So we can vote on which were the most essential ones that you would like to go over.
25.
26. Wait,
26.
26.
35.
26 part B.
30.
30, 30, what was it? 5?
Yeah, 35. But we don't have to go over 30, right? You said that one.
Oh yeah, I don't like problem 30.
Wait, but I want to understand what the
No, it's a dumb problem. I'm never signing it again.
You answered it?
Yeah, you can replace 30 with 30. So the whole area of the paper, don't they just try to like minimize it? Then so there's like
30 just a square. It's just a big
Yeah, I know,
square.
it's so
plus
boring.
1.5.
It's really boring.
Number 26 too, it's like an equal number.
That was like,
Wait, like already like.
It's so boring.
that was like angry. It's great.
All
All right. La la. So we will do 20. Let's talk about 26. 26 is a great problem. Can someone write that backboard also? Someone flip the camera already? Good. 26 was the problem said, find the area of the largest isosceles triangle that could be inscribed in a circle of radius 4. Let's do it. So here is my circle of radius 4. Here is the center of my circle. And they are going to draw an isosceles triangle like so. And unfortunately, they kind of baby you by giving you all of the good ideas for what to do. Like they give you the picture and they sort of choose the variables for you and everything. The radius of the circle is 4. And the key step, I think, that would have gotten some people stuck if they'd not given you the picture, is to draw radii. And then their second really helpful hint is to do it all in terms of a variable h, where h is the distance from the center of the circle to the base of the isosceles triangle. Yeah. So it's isosceles in this sense, and now I would like to find the triangle of maximum area. And all these optimization problems work the same way, which is basically if I can write a function for the area, then I can just maximize that function, and then I can do it. So all right, I have to do a little bit of geometry, but the geometry they have to do is like not that hard. If this is h and this is 4, then this is root 16 minus h squared. And then I think I can pretty easily write a formula for the area of the triangle as a function of h. It's just 1/2 base times height. 1/2 times the base. Well, the base is just twice root 16 minus h squared. So all of that, 1/2 times the base times the height is h plus 4. Cool? Alright, so I've succeeded in writing a function. So what is this function? This function is just h plus 4 times 16 minus h squared to the 1/2. That's all got this far, right? This is the easy part, part A. Okay, and now all I have to do is I can sort of turn my brain off for a few minutes and just differentiate. So let's differentiate, correctly and stuff. So what is the derivative? This is the first times the second. So 16 minus h squared to the 1/2. Plus the first, h plus 4, times the derivative of the second. The derivative of the second is 1/2. 16 minus h squared to the negative 1/2, back inside negative 2h. So see how I do my work all nice and neat and organized, can't possibly make a mistake. Yeah. Simplifying this a little bit more, it's 16 minus h squared to the 1/2 the 2 and the 1/2 cancel, so it's like minus h plus 4, 16 minus h squared to the negative 1/2. And the way that I have encouraged you to do these problems is that to just factor it. So what am I going to factor out? 16 minus h squared to the negative 1/2, says Buses. Yeah, and if I do that, I'm left with 16 minus h squared. You guys getting better at this? Or maybe you are already perfect. Something to the negative 1/2 times something to the 1 is something to the 1/2, so that works. And then I'm just left with minus that. So minus h squared minus 4h. So that's really nice because it leaves me with a polynomial over here in the brackets. And so this derivative is just negative 2h squared minus 4h plus 16 all over root 16 minus h squared. Now just keep working on this. If I factor out a negative 2, it's h squared plus 2h minus 8. And finally, I can write my last expression for the derivative. It's negative 2, h minus 4, plus 4 minus 2, I guess, right? Yeah. Plus 4 minus 2 all over root 16 minus h squared. Okay, cool? Alright, you guys pretty much got this? Alright, let's think about what h means for a moment. What are the possible values of h? No, like what are the, like in general, what's the domain of this function? 0 to infinity? H could be like 10? Yeah, h cannot be, h has to be less than 4. H has to be less than 4 because, like, just duh, right? If you make h bigger, like, if h is 4, we're just out of the circle. Also, could h be negative? Actually? No, I say yes, right? If h is negative, then all that means is that the base of the triangle is like above the. I think it does make sense. I don't think it's probably going to be the maximum area triangle, but I think actually a negative h is actually sensible. It just means if we do it as like directed distance. And you can draw a different picture to make sure that case works, but I think it does in this case. But h can be negative up until negative 4, and then once we get to negative 4, it makes no sense. So I claim that h has to be something between negative 4 and 4. So what I'm now going to do is I'm going to analyze this derivative to see when it's positive and when it's negative. But when I do so, I'm going to draw the number line like from negative infinity to infinity, even though I know that the function's only defined from negative 4 to 4, just because it just helps me do my algebraic analysis to put all the numbers in. So don't freak out, or you could freak out if you want. So there are roots so the denominator is always positive. There are roots at negative 4 and 2. But there's also this negative coefficient, which means it's an upside down parabola, which means it's negative, positive, negative. Keeping in mind that even though I draw this, like some of it's like phantom, right? Like it doesn't really exist. Is everyone okay with this? Sort of rambling a little bit. Yeah. Alright, so the answer is, for the only numbers which are relevant, which is from negative 4 to 4, the answer is that this seems to be the key point. The key point here is at 2. And what is happening at 2? The derivative goes from positive to negative, and thus there is a relative max at h equals 2. And in fact, that relative max is an absolute max, because again, I'm increasing over the entire relevant interval and decreasing over the entire relevant interval after 2. So that relative max is an absolute max. And thus I have solved the problem, because h is 2. Well, if h is 2, and this is 2 and this is 4, then this must be 2 root 3. And if this is 2 root 3 and this is 6, then 6 is root 3 times as much as 2 root 3. So that means this is a 3690 triangle. And that means this is 4 root 3. And if that's 4 root 3 and this whole thing is 4 root 3, then, big surprise, this is an equilateral triangle. Cool? Okay. 26b, move the camera please, is telling you to do the same problem over again, just different and harder. And I know that all teenagers love redoing something that you just did a minute ago. So let's do that now. It's really interesting. Who got this problem, by the way? One. Just one Imogen, that's it. Okay, so here is what? I know, it's like I'm getting even better each year, even though I was already at the 99th percentile. It's like now.
No, but at the beginning when you drew that wax circle, ooh, that was not good.
Good. Good. Thanks for the negative comments. All right, here is the center. I will redraw the same picture. Whoa.
Okay, now we're on our triangle.
And here it is. All right, so what is going on? Same situation. This is still 4. This is still 4. But now they want us to figure out the area of the triangle in terms of a different piece, in terms of this angle alpha. So they call this angle alpha. So now we're going to do like a bunch of trig, right? All right. Well, note that this is an isosceles triangle, and if this is alpha, then this is also alpha. Yeah? Okay. And then, this is the way that I thought to do this problem, at least. If that's alpha and that's alpha, then I can label this little guy right here. What's he? Pi minus 2 alpha. We have to do like radians, right? So it's like the triangle sum theorem just says that the 3 angles of the triangle have to add up to 180, or pi. So this is going to be pi minus 2 alpha. Everybody with me so far? Yeah. Okay, well I can also draw this guy. And then, of course, that's also 4, and that's also pi minus 2 alpha. All right, now you need to just like recall a fact from, or it's at least it's helpful to recall a fact from pre-calc B that you learned, maybe forgot, which is there's like a happy little formula for the area of a generic triangle, given that you know the length of 2 sides and the included angle. Does anyone remember this?
Oh yeah. A, B, sine theta. 1/2 AB sine theta.
1/2 AB sine C or theta.
Yeah, 1/2 AB sine theta or 1/2 AB sine C, yeah. Yeah, and the reason is just because, duh, what's the area of this triangle? Well, if we think of this as the base, then it's just going to be 1/2 base times whatever the height is. And what's the height of this triangle? A sine theta. Right? Of course you are. So now, making use of this formula, I can actually write a description of the area of this triangle. And by this triangle, I mean like this one. Okay, this like triangle. What is the area of this triangle? 1/2. Say it again.
4 over 3. 4. 3.
4 over 3. What are you talking about? No, we're doing the problem all over again. Oh, we can't use that information, otherwise we'd just be
See,
done.
that's why your problem's done.
It's not dumb, it's just redundant. 1/2 4.
4.
4.
Sine of pi minus 2.
Yeah. So let's see what she did. She just applied the formula, right? 1/2 AB sine of the included angle. And then that's also the area of that other triangle over there. Okay? Alright, so now all I have to do is figure out what the area of this triangle is. Well, what angle would seem to be nice if I wish I knew it? What is that angle? Is this how you did it?
No.
Oh. What is this angle?
Maybe like the doubling on and
Maybe. What is this angle though, first of all? I feel like that's not so hard.
Pi minus pi
No,
minus
you should write
that. 4 theta. I mean 4 alpha.
Yeah, right? It just has to be the angle such that these 3 all add up to 2 pi, right? What do I have to make, what do I have to do to make these all add up to 2 pi? Just have to make that 4 alpha. Okay, cool. All right, so I claim that the area of this triangle expressed as a function of alpha is 2 of these triangles, each of which has area 1/2 4 sine pi minus 2 alpha, and then the guy on the bottom, which has area 1/2 4 sine of 4 alpha. And yeah, so much what I got. Right. So this is 16 sine pi minus 2 alpha plus 8 sine 4 alpha. And then there's one more cool thing I can do before differentiating. Calvin, what is sine pi minus 2 alpha?
Sine of 2 alpha.
Good guess. He's guessing, which is sometimes that's important in life. If you don't know what the hell you're doing, just make a guess in the time allotted. Giovanni, figure out what that is. What is sine pi minus 2 alpha? I don't know. There's a million things you can do. You could draw a picture. You could think. You could like move crap around. You could draw a unit circle. You could do the sine of a minus b.
Negative 5 sine.
Good guess. Wrong.
No? But, no.
So do the double angle again.
Sine, cosine, cosine, sine. Oh yeah, I don't know what happened. 0, minus 7. Isn't it? I think it's just sine 2 alpha, right? That's what I got. Oh, it's cosine pi is negative 1.
Yeah, it is.
Oh, negative 1.
Yeah. 2 angles which are supplementary have the same sign. That's just like a thing, right? If that's like x, then and that guy is pi minus x, then they have the same height. Yeah. Okay, so this is actually, the actual formula for the area of this thing in terms of alpha is 16 sine 2 alpha plus 8 sine 4 alpha. I think I'm going to just stop here because this is now, I just don't feel like doing this because I would just be doing it for you, but this is now like hard work complete. I have come up with an expression for the area, and now you just have to like differentiate, do a lot of trig, and then you'll eventually find, what do we think the answer is going to be? Yeah, we're eventually going to find that the area, that the alpha, that this function is maximum, or that this area function is maximum. Hopefully we learn that that's true when alpha equals pi over 6, because that would mean that it's an equilateral triangle, which is what we found in the previous problem. All right, Steve, are you okay with that? Can you just like finish that later or something? All right, let's try to go over one more. I think we have time for like one more. Oh crap, we like don't even have time for one more problem. Let's do one problem super fast. What do you want to do? 35 or 39? You have a choice.
35.
35? Okay, let's do 35. That's more fun. 35 is cone inscribed in a sphere. This is a classic calculus problem. Did we talk about this? I think I must have talked about this in another class. This one year I kept saying over and over again, this is a classic calculus problem. And my class started just like, making fun of me. And that became like this like catchphrase. Like, oh, what are you doing today? Another classic calculus problem? But this one, for real, this is a classic calculus problem. Everyone is doing this problem right now all across the world. Alright, and the problem is, find the volume of the largest cone inscribable in a sphere. This is part of a whole family of problems. Find the largest sphere inscribable in a cone. Find the largest. There's a bunch more. I can't think of it.
Is it a classic family?
What?
Is it a classic family?
It is a classic family, yeah. Okay, good. Alright, so we do it. This is number 35. And the radius is just like r, right? Yeah. Alright, sphere happening. And we have. And we have the center of the sphere here. And we have the cone. Like so. Yeah. Whatever. Cool. Okay, so we have to be very careful now. What we're told is that the radius of this sphere is r. So the brilliant move, the move that you would not probably have thought, or you might not have thought of if you had just been given the problem in word form only, is to connect the radii, which is what you should always do when you're doing problems involving proving things about circles or spheres. Draw radii. Once you draw, but they did this for you because they babied you a little bit. The other problem is that I should not just be throwing around loosely the word radius. Why, Mateo?
I know why.
Uses.
To redo it because apparently the formula for a cone is like 1/3 base squared r or something, or r squared or something like that. It has r in it. That's different from the r of the sphere.
Yes, thank you. What you could have just said simply is that the sphere has a radius and the cone also has a radius, and they are not the same thing, right?
Yeah.
They might be.
So
Exactly.
they might be, but they're not. Okay? They're not. Note that r is the radius of the sphere, and also that r is a constant. Gerhard, r is a constant. It is just simply a number, right? So that's going to come up later when we differentiate. We need to be careful not to like try to treat r as a variable because it's not a variable. It is simply a constant. Okie dokie. How do I complete the picture? Well, they baby you some more by drawing a little thingy in here, which heavily suggests that there is a good idea. And the good idea is pretty much a recycling of the old good idea. And that is to do this all in terms of this variable x. Is this what you guys did?
Yeah.
Raise your hand if you did this. 1, 2, 4.5, 5.5. Okay, this is the good idea. It's not the only idea, but it's the good idea. And so so what I'm going to do is I'm going to find the volume of the cone, and I'm going to find the x which makes that volume largest. Okay, can I go fast now?
Yes.
All right, if this is x, then this is root r squared minus x squared, yeah? And now I'm prepared to write down the formula for the volume of a cone. And the answer is, in terms of x, the volume of this cone is going to be, well, it's 1/3 pi r squared h, as you all learned when you watched my cone volume video. It is 1/3 pi r squared, but r is, it's this, right? Squared. That's actually kind of nice because it just goes away. 1/3 pi r squared h, and h is just x plus r. Cool? Okay, so that gives me a relatively nice formula for the volume of a cone. It's pi over 3 x plus r times r squared minus x squared. And now it's debatable whether I should multiply all that out or do the product rule. I don't know. What do you want to do?
Multiply it out.
Multiply it all out? Should we do what he says? What's up?
Like, can't you just change r squared minus x squared into r plus x, r minus x, plus r squared?
Why would that accomplish?
Because then you just have like an easy product rule then.
I don't know. I don't know what to do. I think I'm just going to leave it as is. Why not? Whatever. All right, so let's differ. Is everyone kind of with me though? The hard part again of the problem is, I think, the drawing the picture of the modeling, the thought to connect radii, that they gave that for you. You have to choose a variable on your own. You have to do it all in terms of that variable. You have to understand that the radius of the cone is not the radius of the sphere. You have to write down the formula for the volume of the cone correctly. Now we can just do some generic differentiation and just hope to not mess up. So here we go. This is root of the first, which is
1
1 times the second